Hey everyone, and welcome to Knowles Marine. Today we're going to go deep, right down into, focus on the Introduction to Naval Architecture, Stability Explained. First up, let's look at what stability actually means. In simple terms, stability is the ability of a ship to return to its upright position after being heeled or tilted by an external force. Things like wind or crashing waves. Now, this ability depends entirely on the relative positions of three crucial points. We've got G for center of gravity, B for center of buoyancy, and M for the metacenter. In this explainer, we're going to cover 5 essential concepts. Number 1, what is GM? Number 2, why is GM important? Number 3, negative GM. Number 4, metacenter. And number 5, stiff versus tender ship. Let's get right into it.
Section 1. What is GM? Let's talk about the metacentric height.
So what exactly is it? Well, GM is literally the vertical distance between the center of gravity, G, and the metacenter, M. It's the primary indicator of a ship's initial stability. The formula is actually pretty straightforward. GM equals KM, which is the distance from keel to metacenter, minus KG, the distance from keel to center of gravity. Now, the results tell you everything. If your GM is positive, the ship is stable. If it's 0, you've got neutral equilibrium. But if GM is negative, oh boy, you have an unstable ship on your hands.
Moving on to Section 2, why is GM important? You might be wondering, why is GM the absolute most important measure for a ship's initial transverse stability? Well, a positive GM gives a ship a righting tendency. That means it has the built-up energy to upright itself after tilting over. At small angles, we calculate this righting moment by multiplying the ship's displacement by GZ. That's our righting lever. Now, while the International Maritime Organization's intact stability code doesn't mandate a universal GM value, we do know one thing for certain. GM directly dictates the ship's rolling period. A larger GM, that means the ship rolls very fast, which results in a shorter, much stiffer roll.
Section 3. Negative GM. What happens next?
So what happens if GM hits the negatives? The situation instantly becomes incredibly dangerous because your ship is completely unstable right from the start. At small angles, the righting lever, GZ, actually becomes negative itself. Because of this, the vessel will just automatically heel over to a completely new angle. We call this the angle of lull. And worse, it will settle into a really dangerous new equilibrium right there.
So what causes this dangerous negative GM in the first place? Well, there are 3 main culprits to watch out for. First, excessive top weight. Second, a high free surface effect, liquid sloshing around inside a slack tank. And third, topside flooding.
How do we actually correct this? Your primary action is to lower the center of gravity to make GM positive again. We can do this by removing top weight or by adding bottom ballast. But listen to me very carefully here. Under no circumstances should you ever try to correct this by filling a slack tank. Seriously, never do that. Always remember that rule.
Section 4. Let's define the metacenter. What exactly is M?
Let's briefly break down what the metacenter actually is. When a ship heels to a small angle, the vertical line passing through the new, shifted center of buoyancy intersects the ship's center line. That exact intersection point, that is your metacenter, or M. The relationship is defined by a simple formula. Bm equals I divided by V. Here, I is the moment of inertia and V is the volume of displacement. Now, because a ship's underwater shape physically changes when it heels, a wider ship beam creates a much larger moment of inertia. So naturally, a wider ship gets a higher M, giving it much greater initial stability.
And finally, Section 5, the difference between a stiff and a tender ship.
So what is the real practical difference between stiff and tender ships? Well, a stiff ship has a high GM, and that creates a very large righting moment. However, this means the rolling period is very short and fast. The result, it's a highly uncomfortable ride for the crew, it poses potential damage to your cargo, and it puts severe structural stress on the ship itself. Now, on the other hand, a tender ship has a low positive GM. The righting moment is smaller, resulting in a long, slow roll. This provides a way more comfortable ride, keeps the cargo perfectly safe, and keeps that structural stress low.
If you found this breakdown useful, give the video a like, share it with your fellow engineers and maritime cadets, and subscribe to Knowles Marine for more detailed deep dives into Introduction to Naval Architecture, Stability Explained. Before you go, consider this.
If a stiff ship is safe but absolutely miserable to ride, and a tender ship is comfortable but has a much lower margin of stability, how would you balance these two extremes if you were designing the next massive cargo vessel? Hit the bell icon so you never miss an upload, and we'll see you in the next one.